when you are. We're good? So we're talking. Okay, let's go. Thank you. So this is week 2, and we'll talk about principles of energy. This is very important to understand, so please give me your attention. We'll talk about a few concepts that will carry with us for the next semester as well, and they're very good to observe, and I want you to understand this because it will change the way you look at energy and how does energy move from one place to another. It's a little bit of physics in a conceptual term way, like it's not too much numbers, just want you to think about it a little bit. I'll talk about the principles of energy and what is happening around us. And it's very important for you as a technician to be aware of these things and give them the proper name and meaning. So we'll talk about, understand what is energy. Where does it come from? Where does it go? And then energy costs you money. So then if you want to put a dollar sign, it costs money, so we have to think about it this way. What is thermodynamics? Seems kind of fancy. It's not. I mean, it's a very simple concept. Thermo means what? Heat. Dynamics? Movement. So something that moves. Dynamic. So thermodynamics is the movement of heat. It's the study of the movement of heat from one place to another. We'll talk about the first law of thermodynamics and the second law of thermodynamics. And it's not that complicated. I'll try to simplify it. And it's happening around us. All these laws are laws of nature. We're just putting some kind of formula to be able to understand them and deploy them to our needs. So what is the first law? We'll talk about that. And what is the second law? And you should know that because you're going to be working with that for the entire time. You might be already working with it. You're just not aware of this is what it's called and this is how it functions. We'll talk about latent and sensible heat. That is very, very important for both residential heat and residential cooling. The AC depends, the refrigeration cycle depends a lot on the second law of thermodynamics and depends on the concept of latent heat and sensible heat. I'll explain that a lot, and if it doesn't make sense, please ask. And we'll talk about something called enthalpy. It's not that difficult. I'll give it a simple name and we'll go with it. So what is energy? So if you think about energy, give me an example. How would you define energy? Sun. Great, thank you. Sun is energy. 99% of the energy we have here on Earth is from the sun, one form or another. If you think about fossil fuel, where that came from? Dinosaurs, okay, and plants, okay, where that came from? Sun. Every 99% of the energy we have here on Earth is from the sun. Where's the 1% coming from?
Us.
Huh?
Us.
No.
Wind, water.
No. It's all sun. Sun move the wind. Huh? For me? No, thank you. No, I don't think so. But the 1% is with the Earth, heat. Huh?
Cosmic radiation?
In a way, it's the Earth cooling from 4 billion years ago.
Okay.
Yeah. So it's from Earth cooling in the internal Earth mantle. That's 1% of them. But everything comes from the sun. Okay, based on that concept, and the idea that energy never get destroyed or come from nothing. So Cass said 99% comes from the sun. Where is it going? That does not destroy. It just moves from one form to another. So if I had food this morning, that's energy, right? I ate banana or something, that's energy. I ate that banana. What happened to it? It decomposed in my body, metabolized, and became energy. I produced energy. But I did not produce it. I just moved from one form to another. If I have no food at all, I will have no energy. I have no energy to lift this folder here, right? So this book has energy. What kind of energy does the book have? Potential. Potential. It's the gravity pulling toward and I'm lifting the book. If I let go of the folder, what happened to the energy? It became kinetic, it moved the book, it hit the table, it generated some electricity, it made that sound. Sound is energy. So it keep moving from one form to another, and I want you to think about that concept as you go along, that energy does not vanish. We just have to put a name and some calculation for where did it go from one place to another. And that is, my friends, the first law of thermodynamics, which state that energy does not get destroyed and does not come from nothing. Simple enough? It seems intuitive, right? Energy does not come from nothing and does not vanish. Money is energy. You work for it, right? You just transfer from one form to another. Food is energy. And food is, what does food does? It gives you nutrients, but it also gives you energy. That's why when you read on the food label, it says calories. What is calories? It's a heat energy. It's how much heat you get out of the food. And what do you need heat for? Just to keep your body alive. So the 2,000 calories they say the average person needs is just to maintain your body heat. Reptiles, they don't even have metabolism. That's why they eat once a year or once a month. And they use the heat sun to metabolize things.
You say reptiles?
Yeah.
So alligators?
Yeah. A snake eats once a year.
So you just eat for fun.
Not for fun, it's once a year, that's what they need. But it does not move much. It gets heat from the sun. Alligator does not eat in the cold because it knows if it eats in the cold, the food is gonna kill it. Because it has not had heat to digest the food. It has to go bask in the sun, otherwise it's not going to metabolize things. Mammals, which is us, we're mammals, we can metabolize food in the cold because our liver can make some enzymes and metabolize food and make heat out of it. How do we metabolize food? Why does sugar has more energy than meat? Because it's simple form of carbon. So the simpler the food, the more energy you get out of it. Heat energy. How do you burn it? So oil. You eat peanut oil. You can eat peanut oil. A tablespoon of oil has 200 calories. That's basically carbon-based fuel that you use to burn slowly and make heat out of it to heat your body. Honey is the same way. I made a comparison one day to compare a Kawasaki Ninja to a human being and see which is more efficient based on gasoline. I'll show you later on. It's very fun. But again, your body uses this energy to make heat, and the 2,000 calories you need is just to maintain your body heat. If you work out using more energy, because again, you need heat, your body heats up, you're expediting the muscle work, so you need more calories. So energy does not come from nothing. You need something. If you do not eat, your body is going to start eating itself. You're not going to have enough energy. And eventually, this energy will transform into something else. It does not vanish. So you cannot just say, it went for nothing. No, if you eat something, it's going to be with you. If you have healthy metabolism, whatever you eat is going to go into your body. Conservation of energy law, that's the first law of thermodynamics. Energy, again, has to go from one thing to another. I'm working right now. I'm making energy. I'm using energy. And the reason we're talking about this a lot is I want you to think when you burn that 1 gallon of oil in your house that is worth 140,000 BTU, where is it going? Okay? Same thing when you eat. If you eat a bucket of ice cream and you don't work out enough, you're gonna know that scale is gonna change because your body's going to, I'm not using this energy, might as well store it somehow. Luckily your body has the ability to store the food into fat. 1 pound of fat is 3,500 calories. So calories are another form to measure heat. What do we use for HVAC as heat? What is our unit? When you buy an AC, what is the units? BTUs. So that's what we use, a BTU. You can convert BTUs to calories. You convert calories to watts, and so on. The unit, just different name for different field, but at the end, we need is heat. Why do you feel less hungry in the summer than the winter? Do you notice that? It's hot. Your body does not need to generate more heat. In the cold weather, your body is struggling to keep the body temperature at 97. Otherwise, you go into hypothermia and your body does not function. So that's why in the winter you need to eat more energy-dense food to keep your body temperature. In the summertime, probably you're sweating, you're hot, your body is not eating enough food because you're already getting a lot of heat from the outside. Okay, that's the first law of thermodynamics, my friends. Easy. Any questions about what does that mean? First law is energy does not vanish, does not come from nothing. Conservation of energy. Again, we go back again from the sun. The sun, at some point, feed the plants. Plants feed the animals. Animals and plants become corpses, decompose over millions of years, become fossil fuel. That energy is still there from the sun. You refine that energy, you put it in your car. What happens to that energy in your car? It burns, it expands gases, it moves your car. Some of that energy moves the car, some of that energy is used to resist the air, and some of it is going to heat. But everything should be accounted for, and you will know where it goes. When you burn oil in your basement for 140,000 BTU per gallon, you want to know how much you're going to get inside the house. Ideally, with some kind of losses, there's always going to be some losses. You will want to get at least 100,000 into your house. If you're getting only 40, that's something is a mess. And you're going to know where did it go. It's a concept. We're not going to do a lot of details into it. I just want you to understand the idea that everything has to be accounted for. It doesn't just go away. Okay? Another created destroyed, that's another way of saying the same thing. Where does it go? It transforms from one form to another, and you got to understand what form does it go to, and how can I put that form into my use. What do you think is the efficiency? Let's assume that the gasoline has 120,000 BTU of energy in it. How much is that transferred into mechanical energy in your car as a percentage? Take a guess.
10.
No, it's too low.
65.
No, that's too
40.
high. Close.
50.
Between 30 and 40.
No.
That's how much you're using out of energy in the car to make it into what you actually want, which is mechanical energy. You don't want the heat from the engine. That's not doing you anything, except in the winter it can heat the cabin, but that's not really the purpose. So that's the reason that you're getting only 35 to 40% of your car, of your gasoline energy into actual dynamic movement. Otherwise, the rest is all losses. Diesel engines are much better. Does anybody have a diesel car? If you have a diesel car, you get 50 miles per gallon. So gasoline, you get 20. Diesel is more efficient than gasoline by nature. So you get more out of it than gasoline. That's why most trucks are diesel, most heavy equipment are diesel, because it's more efficient. What else? So again, gasoline, there's a lot of waste in the gasoline engine. That's why when you go to electric car, what is the efficiency of electric car? 95, 98. You put 100 watts in the car, you get all of it into movement. Some losses for friction, and that's why people are doing the argument that electric cars are more efficient. The other story goes, if you want to argue about that, is how you make electricity. Is that even efficient? So that's another argument. But in theory, electric car, you put 100%, you get like 95, 97, 95, which is pretty good. Gasoline engine, you put 100 BTU, you get 35. So it's not that efficient. It's getting better. There are some scientists working on making the internal combustion engine more efficient, but it also goes into the cost of building the car. Again, we're trying to make it in the sweet spot where people can afford to buy a car that's efficient. Okay, some are useful to us, and some are not. So we're trying to make use out of all this energy. So in the car, in the winter, you're making use of this heat that is wasted. You throw away from your muffler, from your under the hood, there's a lot of heat that you're not using. And if you can make use of that somehow, you will make a better, efficient car. So, does anybody has a car or know about a car with a turbo? Turbocharged? So what does it do? Tell us, Ethan.
Me?
What does a turbo does?
Well, I just bought a car yesterday, so I just know it makes it go fast.
Compresses the air.
No, yeah.
Yeah.
I was about to say.
So you use this waste heat to compress the air and heat the air, so the engine does not have to deal with cold air into the combustion chamber. Yeah.
You wanna cool the air too after it heats it and
Yeah.
then put it in.
Yeah.
The density to be right.
So that's what the turbo does, and it also compresses the air. So you're making use of it's more efficient than a regular car. Why does the name of a car doesn't have a turbo then? It's expensive. Ideally, you want every car to be as efficient as possible, but if you want a very, very efficient car, probably gonna have to spend a lot of money to make it efficient.
All diesels
And,
have them.
huh?
All diesels have them though.
Yeah, that's why diesel is very efficient. Like you can buy a Jetta or a GTI that does 55 miles to the gallon. That's really, really nice. In Europe, most cars are diesel. By law, a lot of them are diesel, and which makes the car a little bit at least $7,000 or $6,000 extra in the regular car. But again, there's a lot of legislation into that, and they are becoming more and more efficient. Back in the days, it was a pain to get the car started in the winter. You have to heat the engine, you have to plug it in, otherwise it will not start. Now they're becoming more and more efficient. So there's no reason not to have a diesel car. But again, we get more out of it than we would. Forms of energy, there's a lot of forms. Potential, when something is hanging that has a lot of potential energy. Kinetic, something that's moving has a lot of kinetic energy, like a pendulum. Pendulum top has potential energy. When it swings down, has kinetic energy, movement. Thermal, there's a lot of thermal energy. If something is hot, it has a lot of energy. Sometimes you can see it gets too hot that it glows. There's so much energy in it. So that's thermal energy. There's chemical energy, something you can burn. Sugary water, that's energy. Gasoline, that's energy. High fructose corn syrup, that's energy. It's a lot of energy in food, and how easy you can metabolize that, how easy you can burn that has a lot to do with it. That's what makes gasoline a more viable fuel than number 2 fuel oil or number 6 fuel oil or coal. It's how easy you can burn that and get the energy out of it. And again, I said 99% comes from the sun, as Cass said, and 1% comes from the earth solidifying, and we can still tap into that by geothermal energy. So again, to repeat, first law of thermodynamics is energy does not vanish or come from nothing. And all the energy in the universe, according to scientists, came from the Big Bang. Somehow something as big as the tip of a pin exploded, has a lot of energy, exploded, and the whole universe came from it. Nobody knows for sure what's happening, but again, according to the results, that's what we can think of. Something exploded, matter came out of it, and all this energy. And I don't know, it's very mind-boggling. It's beyond, it's bigger than my brain, but everything did not come from nothing. And this little seed engine, everything came. And we talk also in the other class about how we still do not know what is mass, what is gravity. Everything is basically a form of energy, and it's all relative. For us, things are solid. We're walking on solid ground. However, for waves, they can go through walls. It's very porous for them. For us, it's relatively solid. So if you think again, back to the electrons, and I think that's how they do teleporting at some point. I don't know, man. Just so many things. But
You could teleport it.
yeah, shit, I guess it's a fish. Yeah. So if you think about it, remember last class we said the electron is basically nothing but some energy and something spinning really fast. So this ground here is basically a bunch of electrons and matter spinning too fast for me, that for me it's solid. Like when you look at the fan spinning. When it spins, you don't see it, right? Looks like it's a sea, you can go through it. So it's all relative. So maybe if your body spins the same speed as the fan, you can go through it. And also, if you look at again a spinning fan, and if your eye vibrate with the same frequency, you'll see it as solid blades. And again, I don't know if any of you guys had something to do with timing belts in the cars. They have this little gun, flashlight, timing light, that will flash as fast as the timing belt goes, so you can see it's solid, because it's all relative. Otherwise, it's completely spinning. So, again, it's a big science, but we have to know that everything is relative. Measurement of energy, that's what we think about for our field. A therm. There's terms. Term is the one, let's write it down. That's 100,000 BTU. Kilowatt, other measurement of energy. Volume of gas or oil. Sometimes you can measure energy with gas or oil. You can convert all forms of energy from one unit to another. You don't have to remember this. It's just information. I don't want to go too much into it. So, the energy transfer, work done, move an electric charge from one column through identical potential difference is known as 1 volt. You don't even need to know that. I just want to convey the idea that forms, energy goes from one form to another. And BTU, in the book they say it's the energy and heat energy in one match. One stick match burner, that's 1 BTU. Or energy required to raise 1 gallon of water by 1 degree. Yeah.
I just recently heard that it was 1 square foot of water, not 1 gallon.
Square foot, maybe it's the same. What does the book say?
I'm not sure.
Okay, we'll double check that. I'm not gonna split hair over it. It's amount of water over 1 degree. Yeah. Which one?
BTU?
Heat energy in 1 match. Stick. No, M.
Oh, it's the match?
Yeah. It's called that right? Or is that the energy?
I'm looking at that and all I see is just like a line.
Well, it's really far. Need binoculars, huh? Whoa! Yeah, I gotta make it bigger. Huh? Okay. Let's tie him over. They can have it in the slides anyway.
What does it say now?
There's nothing.
There you go.
One.
We appreciate it back here.
Literally.
Shit, there you go.
Or energy to raise 1 pound.
It's 1 pound.
1 pound can't spell Fahrenheit, so I'm not gonna be honest. I think I have it here somewhere. There you go. So these are units. BTU stands for British Thermal Unit. Watts is joule per second. It's the same. It's a measurement of unit, and you can transfer from one to another. And what else? Horsepower. 33 foot-pound per whatever. Whatever the fix is. But horsepower is a lot of BTUs. I think 33,000 BTU. So it was here already. I got it right. Energy in one match. Energy is the temperature of water, 1 degree Fahrenheit. A therm is 1,000 BTU. It's okay. The repetition is good. Make perfect. I love to use it. So what is thermodynamics? It's the branch of physics concerned with the heat and temperature and their relation to energy and work. So we call this, there are cycles that has to do with thermodynamics. Combustion engine is a cycle of thermodynamics. There's the Rankine cycle, which is again has to do with heat and work. So what is work? Work is moving something from one place to another, right? So your car is an example of a Carnot cycle, which is thermodynamics. You heat gases, you move a piston, you convert that into work. That's a cycle. We also have what we're going to work on a lot is the refrigeration cycle, which is again same thing. The compressor does the work, it pumps heat from one place to another, and we also use some kind of fluids. Conservation of energy. Again, as Kaz said, sun, living organism, fossil fuel, heat, work, it goes again to heat and landfill. So there's a cycle, things will move from one place to another to a different form, but it will still remain in there. And the reason Earth is full of life is it's because it's the right distance from the sun, and the sun keeps supplying us with energy every day. As we said last week, the amount of energy the sun supplies in one day, if it captured from all the Earth's surface, is enough to sustain human needs for at least 10,000 years. So that's a lot of energy. This energy is moving the wind, it's making the rain cycle, is feeding a lot of plants. So there's a lot of energy coming from the sun, and it keeps recycling. Second law of thermodynamics. So what is the first law? Gas? First law.
First law.
Yeah, thermodynamics.
Can we go back and read it?
Just tell me.
Energy does not come from nothing and is not.
Thank you. Appreciate it. Simple as that. It's gonna be in the quiz. It's gonna be in the final. I'm gonna ask you what is the first law, and please remember that. It's very easy. Okay. So the second law, I'll try to simplify again. So naturally, heat moves from hot to cold. You agree? We agree, right? If you want it to go the other way around, you have to put in some more. You have to pump it. Huh? It's okay. Find the typo. Winter, that's Icelandic, man. That's how to spell it over there. The winter is coming. Winter is coming. So, if you have a cup of coffee, that cup of coffee is hot, right? The heat gonna go from the cup of coffee to the atmosphere, right? So, naturally, heat moves from hot to cold. Everybody agree? But we can make it move from cold to hot. But we have to put equal amount of work. And that's what the AC is doing. The AC is a pump that is pumping heat from the inside to the outside, even though it's hotter outside than inside. Example, water goes from high elevation to low elevation. If you want the water to go from the lake to the top of the mountain, what are you gonna do? You're gonna pump it. If you pump it, you're gonna put some more. So, and that's, my friend, is the second law of thermodynamics, that heat goes from hot to cold, and if you want it to come from cold to hot, you have to put in some work. And you're gonna do a lot of examples in that with AC. That's a little bit confusing with the refrigerant, but this is how we use that cycle to make things cooler. So if we want to move heat from cold to hot, we have to put in equal amount of work. If we want to move 1,000 BTU from a room, we have to put in equal amount of energy in kilowatts, which is electricity conversion. And if you have a 100% efficient compressor, it's gonna be the same, but it's not gonna happen. So it's gonna be a little bit higher. There are some losses. So you have to put the equal amount of energy into that cycle to pump that heat out. So if you want to heat the room by 1,000 BTU, either 0.3 kilowatts or 0.2 of gallon of oil or fuel oil has to be put in there. So again, if you wanna add energy, you have to burn something. You wanna take energy, you have to pump it out mechanically. And that's what the compressor does. Make sense? Anybody's confused? Question?
Can you repeat the second law?
Second law, heat moves from hot to cold. And if you want it to move from cold to hot, you have to put equal amount of work.
Why is it an equal amount? Would that just cancel each other out and not do anything? Or?
No, if you put equal amount, you're moving it from one place to another. Equal or more. So think about it, moving water. You're gonna lift the water, the heavy water, and put it and pump it to the top of the mountain. But the water comes from top of the mountain to the lake, right?
Yeah.
You're gonna pump it from the lake to the top. You have to carry the water all the way to the top of the mountain or pump it out. So it's at least equal or greater because you're gonna be some losses. Questions? And this question is gonna be in the quiz and in the final. I want you to understand this concept. It's not that difficult, and you're already working on it. You're already doing it. And AC is doing this for you all the time. The compressor is sucking electricity to turn the compressor. The compressor is working the cycle to pump in heat from the inside to the outside, even though it's hotter outside than the inside. Make sense? If you want to heat the room, you gotta either burn something with equal amount of energy or produce some heat. So you're gonna put in some, you're gonna burn oil, you're gonna burn wood, you're gonna burn something, or you're gonna use a heat pump that will pump heat from the outside to the inside. So you can use a heat pump at AC if you reverse the AC, and you will heat the inside of the room and cool the outside. And that's called a heat pump. So a heat pump is basically an AC that can reverse. In the winter, it will heat your room. It will pump heat from the outside to the inside. Even though it's freezing outside, it can still pump heat from the outside to the inside. You can always, there's always BTUs, there's always energy unless you reach absolute zero. What is absolute zero? It's 273 degrees Celsius. It's outer space when there's no energy, no heat completely. So we're never going to reach that in Earth unless you're in a large atmosphere to have absolute zero. So if there is some temperature, there is still some heat. So absolute zero probably is outer space, and it's 273 degrees Celsius. I don't know what's that in Fahrenheit. That's when there's no heat completely, and all the molecules stop moving, even the electrons stop moving. Go.
So it's cold in outer space.
Yeah. Bad. Good conclusion. It's very cold. Temperature and heat. So we hear these terms interchangeably. What is heat and what is temperature? Heat is energy. Temperature is how we measure heat.
So heat is what?
Energy. Temperature is a measurement of that heat.
What about like cool?
You can measure that temperature unless you have zero. You all can measure that amount of heat with thermometer. And that's a good question. Is there something such as coldness? No. No. Technically, there is no coldness. There is just heat or lack of heat.
Yeah, exactly.
Yeah.
Less heat.
The complete lack of heat is absolute zero. But there is no such thing as coldness. Huh? the absence. The absence of energy. Yeah. So, think about that.
That's deep.
Hold on. Let's take a moment to understand this. It's very important. So think of heat as the presence, and the cold is the lack of heat. And if you pump all the heat out, you're gonna end up with absolute zero, which is nothingness. I think with that, no, we should kill the music. But think about that, because what we're doing with AC, we're scooping heat and we're dumping it outside. And eventually, if you keep dumping heat, you're gonna end up with nothing, which is absolute zero, which is absolute lack of heat. Good question. Good idea. Too much, or are we with you? Are you with me? Did I lose you?
Oh, we good.
Okay, thank you. So what is entropy? I'm gonna sum entropy because I'm bringing this term because you're gonna use it eventually, one way or another. Not in this class, but in other classes. If you look at this nice fancy chart, you're gonna work for some AC company. Looks very confusing, you know, but you're gonna use that eventually. If you look here, there's something called entropy. So I'll tell you how I understand entropy in my little brain, and you can find your own form and your own definition. For me, I will say entropy is the amount of energy that is useful to us. The amount of energy that is useful to us in any liquid or any substance. 30–40%. Kind of like that. Like what kind of energy like that? The useful energy. The amount of useful energy. Let's put it this way. So what is entropy? I can't believe I put that here. I'm very sorry. I apologize for this. I don't mean to confuse you. But entropy is H, M is mass, P is pressure, V is volume, and U is internal energy. You do not need to memorize that or think about it. Just to tell you where it came from. So, if we talk about energy, if we have capture a box now, cubic foot of this air now. I want to see how much energy is in it. The energy in this little cube of gas depends on how much is in there, right? If it's compressed, it has more mass, it has more energy. You agree?
Yeah.
Yeah. The pressure, if it's compressed, it has more pressure in it, it has more energy, it's pushing against the walls. The specific volume is the density. How dense is that air? How many molecules do we have in that little container? So that's part of it. And internal energy has to do with its composition. Some gases are more active than others. Like if you have helium, that's very noble gas, very not doing much. If you have something like maybe nitrogen, that's different. You have xenon, that's different. They have more energy in them, and that's the composition. So it's defined as the thermodynamic potential, designated by letter H, this one, that consists of internal energy of the system, U, plus the product of the pressure and the volume. What do I need you to know? The amount of useful energy in the substance.
We don't need to memorize that formula or anything?
No.
Good.
What is entropy? The amount of useful energy in substance. And if you look here, the unit of entropy is BTU per pound. How many BTU per pound for this substance? We're not going to use a lot of this. We're going to do practical things. But this is just basic, just so one day you hear about entropy and you say that Professor talked about it a little bit, you can say something about it. But I'm not going to ask you what's entropy. And if I do, please let me know. I stick to my word. I'm not going to ask you about entropy. I'm going to ask you what is, in general, what is the law, the first law of thermodynamics? What is the second law of thermodynamics? Okay? So, shall we do this, or you want to wait till the next class? You feel like had enough?
We gotta do that now.
Had enough? Okay. Thank you.